Right. So far on Matroid, we defined independent sets, bases, circuits, and rank functions. And now we will talk about properties of Matroid. Now, one of the most important and interesting property of Matroid is duality. So you may remember that plane graphs have a dual, and we talked about geometric duals and abstract duals. And in fact, abstract dual is actually a property of Matroid. So let me explain what the dual Matroid is. Okay, so here is a theorem. So that M be a Matroid and let B be the set of bases of M. Now, if we take this B star as the complement of all the elements, all the base, then B star is the set of some matroid. And we say this matroid is M dual. The dual matroid of M. Okay. So what are the examples? So I didn't talk about this uniform matroid. Rn, that's a uniform matroid. So what is that? So it's like EI, where E is 1 up to N, and the set X is in I if and only if sides of X is and most are. So then, so for instance, let's think of this. Use 1, 3. What is that? It's like the ground set is 1 to 3, and the independent sets are empty 1, 2, 3, 1, 2. Oh no, that's it. So these are independent sets. Now, what is a dual? So these are the bases. So the duals are the complement of, the basis of the dual matroid is the complement of the base. So here the basis will be the complement. So 2, 3, 3, 1, and 1, 2. So the independent sets are also all subsets. So U1, 3 dual is equal to U2, 3, right? Every set of size and most 2 is independent. Anyway, let's see why this defines a matroid. And let me remind you these two axioms. So enough to check whether the dual matrix satisfies the B star satisfies B1. So this dual is not empty, and B2 if X is in, if XY is in B star, and if E is X minus Y, then there is F in Y minus X such that X minus E union F is independent. No, a base. Now we need to check these two properties. And B1 is trivial because we knew that this is non-empty. How about B2? Right? So in order to prove B2, we need to prove the following. Right? So B2 means so x, y are in B complements. That means the complement of x, complement of y is a base, right? And right, so this is x, y. So this was E, F. Now, so let's say x prime is complement of x and y prime is complement of y. Then E is in, where is E? E is in y prime minus x prime. And F is, we wish that F is in x prime y minus y prime. So what happens? That means we need to prove the following. Let M be a matroid and if x, y, if maybe it's better to use B1 and B2 so that people are less confused. If B1, B2 are bases of M and x is in B2 minus B1, then there is y in B1 minus B2 such that B1 union x minus y is a base. So if you take x to be E, right? So take like x as E and B1 as x prime, B2 as y prime, then this is what you get. So this is exactly the lemma that we need. So let's see why this is true. Now it's not difficult. So as x is independent, B1 union x has a maximal independent subset containing x, right? And this subset and its size is equal to B1 by I3, right? If it's smaller, then the size will be different. All right, so that's it. How can it be equal? So that means there is y in B1 minus B2 such that B1 union x minus y is independent. So it is a base. Right, so this lemma prove, so this proves the theorem. Okay, so by taking complement of the bases, we get the new matroid, and that's the dual matroid. Then, easy observation, that if you have a matroid and take a dual and then take a dual again, then it's just original matroid. Dual of dual is itself. Now, why is this related to our intuition about graphs? Right? Let's say I have a plane graph G. Now, what was the dual matroid? I mean, dual geometric dual. That is a geometric dual, right? Now, what are the bases of the primal graph, the green graph? Let's say, it's a spanning tree, so this is a base. Now, when you look at the complement, then the corresponding edges in the complement form a spanning tree of the dual, right? So the spanning tree of connected plane graph is a base of the cycle matroid. When you go to the dual graph, the geometric dual, then a complement of the spanning tree become the spanning tree of the geometric dual. So you can see the following, right? If G is a plane graph, okay, let me then cycle matroid of G and take a dual is same as the cycle matroid of the dual graph. And so that's why this matroid dual extend to the duality of the plane graphs extend to matroid. But here, what's more interesting is in a matroid, all cycle matroid have dual, right? So in a graph theory, in a plane graph, I mean we define the abstract dual. I mean this is true if H is an abstract dual. Of G, then we can also see the following. So, but remember, there's a theorem by Whitney saying the graph has an abstract dual if and only if it is planar. But in the matroid world, all matroid have dual, right? So if you take a non-planar graph and cycle matroid, you still have a dual. The only issue is that that dual is not a cycle matroid, right? So that's why it doesn't have a representation as a graph. Okay. Now let's see a few properties of the dual matroid and make something. So anyway, let me define a few terms. We say X is a cobase of M if X is a base of its dual, X is co-independent in M if X is independent in the dual, X is like a co-circuit of M if X is a circuit of the dual. Okay, whenever I put co, like a co, what else? Co-dependent. Okay, I mean that's it. Now let's define this matrix M star G as the matroid, yes, as a photograph G, matroid on E whose circuits are precisely the edge set of minimal non-empty edge cuts of G. Okay, and turns out, it turns out that this matroid is actually dual of the cycle matroid. So let's see why. Why this is true. Before that, maybe it's better to understand the core circuits. Okay. So what are the core circuits? How do we understand the core circuit? X is a core circuit. X is a core circuit. If and only if, of course, X is a circuit of the dual matroid. So what are the circuit? It's minimally dependent set. Right. But what is dependent set? Well, dependent sets are the sets which is not a subset of any base. So X is a minimal set which is not contained in any base of the dual. So let me just write it down again. So it's a minimal set not contained in any. Now instead of base, I'm going to say co-base of M. Now, co-base is complement of base. So something is not a subset of so something is not contained in a co-base. That just means that it intersects the base, right? So X is a minimal set such that X intersection B is non-empty for all bases B of M. Right? If this is X, this is co-base, and co-base, so X is not a subset of co-base, so that means there's an element here. That means the complement of co-base, which is a base, intersecting with X, is non-empty. So X is a minimal set such that X in minimal set meeting all the bases, like transpose. Then what is it? Now maybe it's better to take a complement. So the complement of X is a maximal set such that something is true. So what is that? Complement is a maximal set which is not a subset of base. Okay? not a subset of any base of M, right? Because if you look at the complement of X, yeah, so here's an X. Okay, so here's an X in the complement E minus X, and we knew that base must contain this. That means the complement never contains. Oh, okay. So I should let me modify. It's not a subset. The maximum set that does not contain any base of M. So that means rank of E minus X is strictly less than rank of E. Right? So let's call such a thing a hyperplane. So a hyperplane of a matroid M is a maximal set whose rank not containing a base. Okay, so then this means that E minus X is a hyperplane. Right? So what are the hyperplanes in the vector matroid? Hyperplane in the vector matroid is like, if let's say you have a rank 4 vector matroid, then you take a base and there's a base of 4 elements. If you take only 3 and look at all possible vectors which are spanned by them inside the matroid, and that will form a hyperplane. In a graph, if it's cycle matroid, the hyperplanes are the one that are induced. I mean, like what are the maximal subgraph whose rank is 1 less than the rank of a whole matroid? Imagine the graph is G is connected, then its rank has to be 1 less than the rank of original graph. So you take some spanning tree, delete one edge. Now we have 2 spanning trees. Now for all other edges, if they have ends in the same component, you add it, right? So if this is a spanning tree, let's say I delete this edge, so the hyper edge, now you have those edges as an independent set, and then look at the other edges. So think of this process. I start with the green edges, so rank is 1 less than the rank of the whole matroid. And then for black edges, adding a black edge to the green edges doesn't increase the rank because it doesn't span more vertices, right? So I keep adding those green edges, all the green edges except this, right? So that's the hyperplane. So in the cycle matroid, the hyperplane is really like the complement of a minimal non-empty edge cut. Right? Because if you have a minimal non-empty edge cut, then complement is hyperplane. So that's why, I didn't show you the exact all details, but you can easily see that this is the case if graph is connected. If graph is not connected, you need to look at each component, but it's an easy exercise. Okay, so that's why. So that is the reason that this this matrix M star G is actually the dual. So this matrix is called the bond matrix of G. Okay, and a matrix is, we usually say matrix is graphic if it is cycle matrix, and co-graphic if it is a bond matrix. All right, so I've explained you the type, the property of circuits, co-circuits. Now, what the one missing things, the rank function, right? Remember, the rank is the maximum size of independent subsets of something. So here's the lemma. Let M be a matroid with the rank function R, then the rank function of M dual is this. Sometimes it's difficult to remember these signs, which one to subtract, which one to add. But you can, first of all, you can easily see why this obviously satisfies easy cases. For instance, if X is empty, then size of X is 0 and rank of minus rank of M and plus rank of M, right? So this is 0. If X is everything, so if X is equal to E, then it's going to be equal to E minus rank of M, which is the rank of the dual. So this is correct. If X is a cobase, then what you get is size of cobase minus rank of everything plus rank of base. So it's equal to size of cobase. So that means cobase is independent in the dual. So for 3 obvious choices of X, it works. I mean, of course we have to prove it for all general X, right? Right. So how do we prove it? Suppose, okay, I mean, let B be a base of M such that B intersection E minus X is equal to rank of E minus X. Right, so here's X and here's E minus X, and I chose a base B so that this is a maximal independent set of E minus X. Now, that means this implies the rank of the dual matroid. I know that the complement of B is a base. So this is a base of the dual matroid. Right? So that means the complement, the R star of X, the rank of the dual matroid is at least x minus b, right? And which is x minus b intersection x, right? And how do we normalize it? Well, okay, let's x minus b, right? I've subtract all of them, and then plus b minus x. So this is equal to size of x minus size of rank of m plus rank of e minus x. So this proves the one in one direction. The left hand side is at least the right hand side. How about the other directions? Let b prime be a base of m such that the rank of the so that is, now this is like, there is a base, so whose complement has same size as the rank of the dual matrix, right? Inside X. So X intersection E minus B prime. Okay? So again, same picture, but this is B prime. Now, this is, we chose that this is same as the rank of the dual matroid in X. I mean, rank of X in the dual. Now, that means rank of E minus X. What can you say about rank of E minus X? Right. It's at least size of E minus intersection with B prime, right? Because this is independent set. And what is it? Well, another way of saying it, well, B prime minus X intersection P, right? And size of B prime is equal to rank of M minus X intersection B prime. Well, same as cardinality of X minus X minus B prime, right? And that is X intersection E minus B prime. And we know that this is equal to rank of M minus X height of X plus rank of dual, rank of X in the dual. So what does that mean? That means this is less than or equal to X minus rank of M plus rank of E minus X. Okay, so this proves that this function is indeed the rank function of the dual matrix. Now we talked about the dual, so we extended at least one property of the graphs, plane graphs. Now let's talk about minors. All right, this deletion is easy. So, I mean, how do we define deletion? For a subset T of E, we define M delete T be a matroid on E delete T such that X is independent in M delete T if and only if X is independent in M for all X subset of E minus T. So in other words, if M is EI, then M prime is E minus T, and then it's set in I where X is subset of E minus T, right? Or maybe I could say it this way: X is a subset of E minus T such that X is in I. So this is deletion. So this is called deletion, and we also write M delete E for M delete E for elements in EM. So what are the examples? So for instance, if I have a house G, then cycle matroid, we know what it is. And if I delete an element E, then what's going to happen? Well, the independent sets are precisely the same independent set, so it's just delete this edge, right? Oh, yeah. What I mean is this. So deletion just works out nicely. But how about contractions of the graph? How do we define contractions in a matroid? And that's where we use duals. Remember in the abstract dual, the deletion in the plane graph, no, deletion in G corresponds to the contraction in the abstract dual. So we do the same way. We do that thing for matroid. So for a subset T of E, we define contraction as first take a dual and delete T and take a dual again. And this is called the contractions. Or we are saying contracting T. All right. And then N is a minor of M if N is equal to M delete X contract Y for some X, Y, and their disjoint. Now it's easy to see that if H is a minor of G, then the cycle matroid is a minor of the cycle matroid of G. So you can see that the many theorems on graph minors could be extended to theorems on matroid minors. Now, before going into the more, maybe I will show you the rank function of the contractions. Right. So what is the rank function of M contract T? All right. So here's a lemma. M be a matroid and T be a subset of E, then R, let me just say R prime is X union T minus rank of T is the rank function of M contract T. So proof. Why is this the case? Right? So just remember that this is equal to M delete this thing, right? So R prime of X is equal to rank of okay, let me just use that size of X minus rank of M, this thing, right, plus rank of the complement. The complement is E minus T union X, and the complement in this matroid. Right? I'm using this formula. Where is it? Yeah, here it is, right? So rank function of a dual is given by that. So this is it. So this is rank size of X minus, so rank of this matroid is equal to rank of this set, right? None, E minus T. And plus, what is that? Well, the rank of deletion doesn't change the rank function, so that's it. Now, let me put those things. So E minus T minus rank of M plus rank of the complement. So complement is T. And here's rank of the size of this thing minus rank of M plus rank of the complement. Right? And you will see that everything cancels out. Right? So these three cancel each other. So what's left is rank of X union T minus rank of T. Alright, so that's the rank function of the minor, which you can obtain by contractions. And you can also talk about circuits. What are the circuits? Maybe for this course let's not do too much. All right. I think I will finish today's lecture here. So in the next lecture, we will prove the matroid intersection and union theorems, which will imply one of the lemmas we need to prove the Noether A-flow theorems. Namely, we use the fact that if graph has two Ks connected and it has Ks disjoint spanning trees, and there are graph theoretic proofs known, but the proof using matroid is shortest and it's beautiful. So I will show you that proof by using matroid in the next lecture. Okay.